Welcome back. I'm Dr. Nuo Xu. A one-sentence preview of this lecture will be how to predict a target variable with one or multiple attributes with mathematical functions. The core notion underlying this lecture is parametric modeling, which consists of a number of interlocking concepts. To gain a complete understanding of them in algebraic terms is very time-consuming and can be at times quite challenging. Fortunately, their geometric or graphical representations offer a shortcut to a level of understanding that is attainable while sufficient for you to communicate between business units and data science team. Therefore, our emphasis here is to describe these interlocking concepts with a graphical approach. We'll discuss the following topics sequentially: parametric modeling, linear discriminant, support vector machine, logistic regression, and neural networks. It's absolutely essential to make sure that you understand two-dimensional and three-dimensional scatter plots before we get started with our discussion on parametric modeling. So let's work on a few examples together first. Example 1. We have previously produced scatter plots given data in a table format. Here I want you to do the reverse. Given the following scatter plot, where pluses representing good accounts and dots representing bad accounts, can you represent these points in this two-dimensional Cartesian coordinate in a tabular format? Only use those few points with coordinates to demonstrate the approach. Now, please pause the video and work on this. You should get something similar to this table. Notice the table has two attributes and one target variable. So if we call each column a dimension, it actually has 3 dimensions, but it's represented in a 2D scatter plot here. So instead of using pluses and dots to differentiate bads and goods, we can also use a third axis, the vertical axis, to represent the target variable in a 3-dimensional scatter plot, like this one here. If you are not very comfortable reading a 3-dimensional scatter plot, see if the following visualization tricks will help. Imagine the graph on the left as you staring down at the bottom of an elevator, or here, and the axis of the target variable would correspond to the up direction of the elevator. And since the dots are bad accounts and they are denoted as 1, they will ride the elevator 1 floor above here. And the pluses are the good accounts denoted as 0, therefore they will stay at the bottom floor here. Let's now examine this 3-dimensional scatter plot a little bit closer. If we look through this elevator from the angle that is parallel to H, like from this direction, we should see something like this graph on the top right, which we have seen a few times before. A 2-dimensional scatter plot between the target variable and one attribute, balance in this case. Similarly, if we look through this 3-dimensional elevator from an angle that's parallel to balance, this direction, we will see something like this graph on the bottom right, i.e. a 2-dimensional scatter plot between, again, the target variable and one of the attribute. In this case is the H. Now if we want to predict the probability of being bad or 1, using the attribute balance, how would you go about doing it? By examining this graph, we see below a certain point of balance, the probability of being bad or 1 is 100%. And above a certain point of balance, the probability of being bad is 0%. And we should be able to find a point of balance that is associated with the probability of being bad equal to 0.5, 50%, maybe somewhere here. So imagine if we have a lot more instances, we should be able also find a point of balance that will correspond to a 75% chance of being bad and 25% chance of being bad. They could be somewhere here and here respectively. Now if we connect all these points together, it would form a S-shaped curve like this one, which would describe the probability of being bad using the attribute of balance. To be more precise, S-shaped curve should look like this. So this is a S-shaped curve in reverse. So similarly, we should be able to find a curve similar to this one to describe the probability of being bad with respect to the attribute of age. It might look something like this. Now, if we want to predict the probability of being bad using both balance and age, it's also possible that we can find such S-shaped ribbons in this time that consists of a sequence of curves put together parallelly, like these. Again, if you need some help with the three-dimensional visualization, you can think of this S-shaped ribbon as water flowing down the Niagara Falls. Once we found these S-shaped curves or ribbons, we can use them for class probability estimation. So this is the basic idea behind logistic regression in a graphical representation. So how to find these curves and ribbons requires the understanding of parametric modeling. Let's briefly rehash on the first type of model we have introduced, the decision tree, which is really just a set of if-then rules. The graph on the left is a decision tree represented in the instance space. Notice the recursive partitioning corresponds to using only vertical or horizontal lines to partition the instance space for segments of reduced impurity. Now, if we are not limited by using only vertical or horizontal lines, by visualization on the graph on the right, we can use a line like this to partition the space into two segments. Now our classification rules becomes, if an instance is located above the line, then it's a good account. If an instance is located below the line, then it's a bad account. The benefit of this new type of classification is immediate. For one, we only have one misclassified instance here, whereas in the decision trees we would have 4 misclassified instances. The line also lends itself better for class probability estimation, because it seems reasonable that I can draw a sequence of parallel lines that are parallel to the boundary, like this, and they should correspond to an increasing probability of being bad from top right to bottom left. Therefore, it provides more granularity for class probability estimation, whereas in decision tree, each leaf node, i.e., each segmented space, share the same estimated probability, i.e., this place, this instant, and this instant will share the same estimated probability. But these two instances, using this kind of classification, should have really different estimated probability of being bad. This type of line, in this case, is one example of the second type of model that we will be dealing with in this course, i.e., a mathematical model. We have talked about how to arrive at the decision tree, i.e., we're using information gain to select attributes and apply recursive partitioning. So the topic of parametric modeling is about how to arrive at the second type of model. In this particular case, how to find this line that does such a nice job of separating goods from bads. This line is also known as a linear discriminant. There are four interlocking concepts about parametric modeling that we need to understand. They are model, parameters, objective function, and an algorithm to optimize the objective function. I will use the Excel sheet to demonstrate these four concepts. In this Excel sheet, we have three sets of points in this scatter plot. Set 1 are the instance of the red class. Set 2 are the instances of the green class. And set 3 are points that forms the line. Our goal is to move the line to separate the class red from the class green perfectly. Now let's pretend we are machines. We didn't know what an equation like this means. We didn't know what intercept or slope mean either. All we know is by changing these two values, the line somehow moves accordingly. Now let's try a few different values for the intercept and slope to get a feel of it. After a few trials and errors, I noticed that I can move the line up and down by changing this number. I can rotate this line either clockwise or counterclockwise by changing the second number. Now I want you to pause the video and open this Excel file. Now your goal is to find the right values of intercepts and slope by trials and errors, so that the resulting line will separate the two classes perfectly. And in the discussion board, I want you to share two things. Number one, all the different value combination that you have tried before you get the perfect line. Also show a screenshot of the line for each intermediate steps before you find the perfect line. Number 2, I want you to share what are the rules that govern your choice of value, i.e., what is the algorithm you apply to find this perfect line by trials and errors. So now in the case of a linear discriminant, the model is a line which is controlled by 2 parameters, intercept and slope. Our goal is to adjust the value of the intercept and slope so that we can minimize the number of misclassification. A perfectly separating line will result in 0 misclassification. We refer to this goal as objective function in the parametric modeling jargons. We also need to have some clever rules or procedures to follow so that we can achieve our goal. So we call these rules or procedures an algorithm. We'll come back to this important topic of algorithm in a later lecture. And also, since it's the computer, i.e. the machine, that carries out this algorithm, as opposed to you, a human who applied your rules earlier for the Excel example, we call this type of pattern discovery machine learning. Now let's look at another method of classification called the support vector machine, which differs from a linear discriminant in the objective function and the algorithm. Now let's look at the graph on the left. All these lines have 0 misclassification. Therefore, all these lines are equally optimal with respect to a linear discriminant. But look at the graph on the right. Intuitively, this line that has the greatest margin between the 2 classes should generalize the best when we apply this line for prediction for new instances. And that is the objective function for support vector machine, which is maximize margin between 2 classes. It requires an algorithm that uses some very involved math to maximize the objective function. Notice here we use the word optimize or optimization to include both maximization in this case and minimization in our early case for the linear discriminant. Also, the reason that this classification technique is called support vector machine is because the boundary is determined by a few instances that are closest to the border, like these ones here. An instance is also referred to sometimes as a vector. Therefore, the optimal line plus the margin is somewhat supported by these vectors. Hence the name support vector. And of course, the machine part comes from machine learning. Let's now use a model that is slightly more complicated than a straight line. A S-shaped curve that is capped between the value of 0 to 1. Let's go back to the same Excel file for demonstration. In this Excel sheet, we also have 2 sets of points. Set 1 is the points between a target variable and an attribute. Set 2 Set 2s are points that form this S-shaped curve. Set 2 points are described by this equation called a logistic regression. It can express in either this way or this way. It looks very complicated and involves exponential function. But again, for our conversation purpose here, we only need to know this S-shaped curve is controlled by two parameters, the intercept and slope. Again, let's try a few numbers to get a feel of it. So we notice by changing these two numbers, we can control where the center of the curve is located, also the degree of the steepness of the curve. Now, what is our goal this time? To find the right curve to describe the data. The answer to that question is not as obvious as in the case of a linear discriminant, where an optimal line is the one that separates the two classes. However, remember we can construct another S-shaped curve based on the actual data sets, as shown in the beginning of this lecture. Let's now work it out with this data set. So it seems up to 20, the probability of being 1 is 0. And above 60, the probability of being 1 is 100%. Now we can also estimate what is the probability of being 1 between 20 to 30. By counting how many instances have the target variable of 1. So in this case, out of 10, there's only one instance that has the target variable of 1. Therefore, the probability of having the target variable of 1 in this range is around 10%. Similarly, we can work out the rest. Between 30 and 40, there are 5 ones and 5 zeros. Therefore, it's reasonable to assume within this range, the probability of being 1 is right here, 50%. Between 40 and 50, out of 10 instances, only 2 are 0. Therefore, 8 of them are 1s. Therefore, within this range, the probability for the target variable to take on the value of 1 is about 80%, which is right here. Here it will be 90% in this range. So now if we connect all these points, it should form a curve that looks like this. Close enough. Now we know our goal, the optimal curve that we are looking for will be we are trying to adjust the blue curve, which is described by this logistic function, the model, to match the red curve, which is the probability curve that we derive from the actual data set. Now let's try a few numbers to see if we can move the blue line a bit closer to the red ones. Close enough. So it's actually not easy for us human to do it, but fortunately machine can try millions of combinations like these in the split of a second. So now officially matching the blue curve with the red curve is associated with the objective function called maximum likelihood, which requires another clever algorithm to maximize. As we briefly described in the beginning of the lecture, if we want to use two attributes for class probability estimation using logistic regression, we just need to put together a sequence of parallel S-shaped curves to form a ribbon or a surface like this, shown in this bottom graph. The top graph shows a logistic regression model actually has an linear discriminant model embedded in it, shown as this solid line. The direction that is perpendicular to this solid line, shown as this dash arrowed, points out the direction where the probability of being bad should increase most quickly. And we are placing the sequence of S-shaped curve along this direction. And also notice the number of parameters increased by 1 because now we need to have a second slope for the second attribute. What is very remarkable about logistic regression is the same idea applies to more than two attributes. In fact, we can use logistic regression for as many attributes as necessary. This set of graphs shows why you will hear this phrase a lot in data science related conversation, i.e. feeding a model to data. Using logistic regression as an example, we can adjust the parameters to change the direction of the linear discriminant, to shift the center of these S-shaped curves, to stretch the curve to make it more steep or less steep, to best match the probability curves exhibited in the data. And that's why it's referred to as feeding a model to data. Now I'm leaving the last topic of this lecture, neural networks, as the second discussion topic. Neural networks are essentially multiple logistic regressions put together. If we think of a logistic regression as one stretchable ribbons, then neural networks are many ribbons that can be moved, stretched independently, and superimposed on top of one another to form more complicated surfaces. The following two figures, this figure 1 and figure 2, capture the essence of how neural networks work. So far, you should be equipped with sufficient geometric understanding to have an educated guess on what each figure is trying to convey. So in the discussion board, write a short paragraph on each figure to explain how neural networks can classify. In this first figure, one class is sandwiched by the other class on both directions. And in the second figure, instead of having binary classes, we have 3 distinct classes for the target variable to classify. So this concludes our lecture on prediction using mathematical function.